Welcome to the second part of Introduction to Thermodynamics. In the first lecture, we saw some fundamentals. We will continue to see some more fundamentals in this lecture. Let's understand what is thermodynamic system. System means it's a large box, right? For you in an analogy sense, system means like AC unit is a system, right? So, thermodynamic system will have so many ingredients into it. So, let us see what are they. Thermodynamic systems are regions in space whose thermodynamic properties are of interest. If I am going to talk about a building, inside a building I am going to keep a refrigerator at a corner. My interest is only at the refrigerator corner. So, then what do? I try to talk about the thermodynamic properties in the area of interest. So, when you try to expand, you can try to take a larger room, AC of a room, that is also okay. It is a part of the universe that is separated from the surrounding by real or hypothetical boundaries. So, you can see here, this is a system. This system is separated from the universe by a boundary. So, that is the limitation you say. So, surrounded by real or the hypothetical boundaries. For example, if I have a refrigerator, so then that this box becomes a boundary to rest of it. And why is it important? Let me tell you. Suppose let us assume this portion is a cold portion and then you have air coming outside. This air has a relative humidity of maybe 90%. That means to say there are a lot of water in the surrounding air. When it touches the cool system, it tries to condense and form droplets. This phenomena you will try to see when you try to take a glass tumbler, fill it up with a cold water, you will see just around the boundary, you will see droplets of water getting condensed, right. So, this boundary is very important. If you can insulate the boundary, then you get a different performance. If you do not insulate the boundary, there are losses. So, now these thermal losses will lead to energy inefficiency. So, the boundary is also very important, right. So, it is the part of the universe that is separated from the surrounding either by real or by hypothetical boundaries. The surrounding contains everything other than the system, including other thermodynamic systems. For example, you are trying to keep in a refrigerator, you are trying to keep the focus only on the freezer. If our focus is the freezer, then we will everything else outside the freezer boundary is called as a surrounding. So, in simple terms, universe is equal to system plus surrounding is the universe. The nature of its wall characterizes any thermodynamic system. You can insulate it, you can leave it open. These walls can be purely hypothetical when describing them as permeable to all matters, radiation and energies, or it can be real, which can be made of some matter. For example, you can fix a thermocol around the glass and then you can try to insulate the glass. The boundaries of any thermodynamic system can be classified into fixed boundaries and moving boundaries. Fixed boundary and moving boundary. It is very important because later when you go for a higher end computation or higher level courses, they will always talk about fixed boundary and moving boundary. So, when the system boundaries cannot move and remain rigid, it is called as fixed boundaries. For example, a freezer, the dimension of the freezer is fixed. So, the freezer is a fixed boundary. Movable boundary is when the boundary of the system can move. For example, if you have a car which is traveling at a speed, assuming there is a hot body surrounding the car, now the car is moving very fast. So, now it becomes a moving boundary, right. So, these two cases are completely different. For example, you try to take a hot rod, you keep it as is condition, you will see when does the red hot rod become cool. The other way around, you just whip it or you just move in free air, you will see the hot rod will settle down very fast. Now what you do, you take the hot rod and you immerse it inside an ice pack. You will see what is the performance. And then last thing is, you try to do it moving and try to do it in a cold winter day. You will see what is the performance. So the moving boundary plays a different, completely different phenomena. Other than the above classification, you have two more classifications. So they are nothing but real boundary and imaginary boundary. A tangible separation wall that separates the system from the surrounding is a real boundary. So fixed boundary, moving boundary condition, then real boundary condition and imaginary condition. Why is this imaginary very important? Because you cannot try to simulate the complete system. So what we do is, we try to take a small unit cell, and that unit cell we try to simulate and then find out what is the response. So there what we do is, we try to go for imaginary boundary condition. There are no real separation between the system and the surrounding. There is just a hypothetical wall separating the system from the surrounding. You have a body. So now what is happening? You are there, and then you have a boundary, right? You have a boundary. So that is how the thermal imaging works. When you try to use a thermal imaging, our body radiates heat, right? When it radiates heat, when you try to take an image, you will see a boundary which is there, which can radiate heat. You will see a red hot boundary around me. So that is real. Imaginary is, you are trying to introduce something, and wherein which you can try to put a boundary condition. You can try to say, okay, the heat is getting dissipated at some rate, you can try to say. So these are four very important things you should understand. So there are different types of thermodynamic system. So here with the thermodynamic system, so we saw this is a system. So universe is nothing but system plus the surrounding. Now what are we trying to do? We are only first trying to understand what is this boundary. Now we will try to look at the system itself. There are three different types of systems. So the thermodynamic systems are the region in space that are separated by boundaries, which we have clearly established. Again here, boundaries, four different types. And the nature of these boundaries define how mass and energy transfer across the thermodynamic system and the boundary happens. The boundary, because this fellow is the separation between the system and the surrounding. So now the nature of the boundary defines how mass and the energy transfer, heat and mass transfer, mass and energy transfer happens between the system and the surrounding. Every thermodynamic system in the universe can be classified into three types: open type, closed type and isolated type. Predominantly, you can have subsystems in it, right? Open system, if the thermodynamic system can exchange both matter and energy with its surrounding, then it is called as a open system. We will see the example in the next slide. What is a closed system? Closed system means the thermodynamic system can exchange only energy with its surrounding. That is closed. Open system is both matter and energy, right? Closed system is only energy. And the isolated system is, there can neither be a transfer of matter nor energy, is called as isolated systems. Why are the three important? Because when you are trying to work on very low temperatures, we always look forward for an isolated system. We always look forward, because now there are a lot of reactions which happen at very low temperatures. There is, Martin said, when you do heat transfer, there is a big heat treatment process which is happening. When you go below the room temperature, you go down sub-zero, you go there and you try to do heat treatment. It tries to help in freezing the microstructure. So we go for 90% isolated system. So there are three different types of system: open system, closed system and isolated system. So we will try to see the example. So if you try to see that system, open system, closed system, isolate, then matter interaction yes, and in closed system no, and isolation also no. So in the open system, when you talk about energy yes, and in closed system we talk about energy yes, and isolated system both are no. This and this are no. Okay. So what is the mass transfer? What is energy transfer? Mass transfer is, suppose let us assume you have a cooker, prestige cooker, or you have a pressure cooker. When there is a weight which is sitting on top of it. There is pressure goes very high, there is a push which happens, then there is a mass which is moved. Right. So, that is mass transfer. So, energy transfer is the higher temperature, lower temperature, there is a transfer of energy which is happening. So, open system, in an open system, matter and energy can transfer between the system and the surrounding. For example, you try to take a tawa, a pan, right. So, you apply energy, you put matter. So, for such system, the boundaries that separate the system and the surrounding allows the matter and energy to pass through it. For example, a tea in a cup, a vapor of heat that go outside the cup and the heat is transferred through its boundaries is a typical example for a open loop system. Okay. So, a tawa whatever you use, it is also an example for a open loop system. Another example is the human body. When we are an open system, because we take energy in the form of radiation and also exchange the heat with our surrounding through our skin. And to survive, we eat, the matter enters and exits our body. Okay. These are very crude examples, but just for your understanding, I have just put for open system. One is an example of a teacup and then the other one is a human body. So, human body radiates. That is why we always try to insist that when you are sleeping during the night time, you should try to maintain a temperature of 24 or 25 degrees Celsius, because our body operates at 32 to 34 degrees Celsius. Then the room temperature, if it is 18 degrees Celsius, then so much of work has to happen through the skin and that will make you tired. So, in order to have a cool setting, we are expected that we set the AC temperature to 24. That is what Government of India is also given under the energy initiative schemes. Okay. Because we take energy in the form of radiation and also exchange heat with other surroundings through our skin, right. So, your temperature is high, the external temperature in a AC room 18 degrees, it is very low. So, you start rejecting heat. Okay. A controlled volume and a controlled surface. A large engineering problem involves mass flow in and out of the system and therefore, are modeled as controlled volumes. Any engineering system will be always try to be modeled as a controlled volume system. A controlled volume refers to a defined volume on which attention is focused for energy analysis. Right. So, you have a system, there is a boundary, there is a mass in, there is a mass out, then there is a heat in, there is a heat out. So, this is a system. So, we try to call it as controlled volume. What are the examples? Example is nozzle, diffuser. Nozzle is focusing, you have something coming up. So, you try to focus through the nozzle, increase the pressure. Right. The area is small, the volume is constant. So, you pressurize it. So, you get a higher pressure air or water coming out. Diffuser is vice versa. Turbines, compressor, heat exchanger, de-superheaters, and then throttle valves, IC engines, all these things follow controlled volume. What is controlled surface? The closed surface that surrounds the control volume is called as the controlled surface. So, you have a control volume, a turbine is there and then you try to close it, right, you try to close it. So, then there is a Q which goes there. So, then it tries to do a work and C comes out of it. So, control surface, the closed surface that surrounds the control volume is called as the control surface. Mass as well as energy crosses the controlled surface. Mass as well as energy crosses the control surface. Please keep that in mind. So, turbine generally we will see little later. Turbine is what happens is you try to push a high pressure, that is what a nozzle is used. High pressure steam is pushed. So, then there is a turbine blade. So, that tries to rotate because the pressure is very high. As and when the work is done, the pressures fall down. So, then it is what it exits out is called as low pressure steam. So, high pressure steam, it rotates. If the pressure or the steam, the weight of the water which comes inside is very high, then the amount of energy which can be transferred to the turbine is very high. So, accordingly the shafts will rotate very high. So, you generate electricity or you generate whatever it is accordingly. right? The control surface can be real or imaginary. Control volume and control surface. Now let us go into closed system. Where are we coming? So open system, we saw a tawa, you saw a pan. So this pan can be dosa pan, or it can be pan for frying, everything it can be there. So that is what it is, or it can be a cup of coffee. It's an open system. Now let us see closed system. Closed system can only exchange energy with the surrounding and cannot transfer matter to its boundary. So you have a pan, put a lid on the pan, right? A closed system can only exchange energy with the surrounding and cannot transfer matter through its boundaries. For such a system, the mass of the system remains constant and the boundary is real, but it can be movable or rigid. The boundary is real in a closed system. For example, when a cap is present in the water bottle, it behaves like a closed loop system. Or you try to buy a Starbucks coffee where you put a lid, it's a closed loop system. Here also you can try to take it to the analogy of open loop, but open system, but just give an example of a closed system. So a system can also change its type with time. System can also change its type with time. So open system, closed system. For example, in case of a car or a bike engine, when fuel enters into the piston cylinder arrangement, we can say that the piston cylinder engagement is an open system. But the same system becomes a closed system when the piston is moving in forward or backward direction. Very important. Please try to see the difference between open system and a closed system. When the fuel enters into the piston cylinder arrangement, we can say the piston cylinder arrangement is a open system. What is a open system? Open system means it is here. There is a matter interaction, there is an energy interaction. But the same system becomes a closed system when the piston is moving in forward and backward strokes. So what is closed loop? Go back. Closed loop is no matter interaction, energy interaction, yes. So a system can move from open to closed, closed to open. What are isolated systems? Isolated systems are those systems in which neither matter nor energy transfer from the system happens. For these systems, the total energy remains always constant. A closed loop system, energy in, energy out. So this is a system boundary. So you can see here mass in, mass out, energy in, energy out. This is open system. So here in the closed loop system, there is no energy transfer happening or no mass transfer happening, but it is a system which is there. So for example, the universe is the most common example where the energy remains always constant. So now you can clearly distinguish open system and isolated system. Mass in, mass out, energy in, energy out. No energy transfer, no mass transfer. That is isolated system. A thermo flask can be considered as an isolated system if it is completely insulated. So you pour into water inside a thermo flask and you keep it for long, or put an ice, keep it for long, it is considered to be an isolated system. Whereas when you try to put the same ice in a glass tumbler, then it becomes an open system. So isolated system, thermo flask. Thermo flask is an isolated system. It is a type of insulating storage vessel that keeps the hotter or colder items at its respective temperature for a longer time. So you can see here the flask, whatever thermo flask, whatever we use, it will have a cover on top, then you will have a cap. So this cap and the cover tries to make sure that there is no heat losses. Then there is a glass, right? Glass which is there, and that is called as a silvered surface. So inside a silver surface, you pour the content, whatever it is, coffee, tea, whatever it is. This silvered surface is again placed in a case. So you doubly make sure from the silver case there is a lot of reflection which is happening and nothing goes out, and if at all something goes out, there is an insulating case which comes. Between in the silver surface also, you have two layers, one layer and the two layer, right? So this is something like this, two wall. So this is inside, this is outside. So between this also they try to create a vacuum so that there is not much of heat loss. So there is a vacuum, that's what we said, vacuum, and then we also have an insulating support so that it is little above the base. So, this is a complete isolated system. So, there is no mass transfer, there is no energy transfer. It is a type of insulating storage vessel that keeps hotter or colder items at its respective temperatures for a longer time. So, it is a isolated system. If you keep the lid open, this lid and this lid open, then it becomes an open loop system. So, think about it. Can you make it as a closed loop system? Just think about it. Now, let us get into thermodynamic properties. Any observable characteristics required to describe the condition or state of the system is known as thermodynamic property of a system. So, there are two things. The observable characteristics requires to determine the condition, hot, cold, condition, right, or a state of the system is known as thermodynamic property of the system. So, we use some of the properties. Specific properties is nothing but extensive property divided by mass is nothing but specific property. Some of the examples is specific property, the property you replace it with volume, you replace it with enthalpy, you replace it with entropy, you replace. So, then every time it will be divided by whatever is the property divided by mass, right? That is what we have said. So, specific volume means it is a volume divided by mass. So, you try to keep 1 kg of something of ice, you keep 1 kg fixed. So, then you can try to have a volume different. Same way with respect to enthalpy, same way with respect to entropy. So, henceforth you should keep in mind V represents volume, H represents enthalpy, S represents entropy, right. So, small v is volume. So, specific volume means a large V means its volume. If it is a small v means a specific volume. If it is a large H means it is enthalpy and a small h means it is specific enthalpy. A large S, that means to say a capital S entropy and a small s is specific entropy. So, you should keep this in mind when we use the convention. Okay. When we talk about properties, there are two types of properties for any given material. One is called as intensive property, the other one is extensive property. Intensive properties are properties which are independent of mass. Independent of mass is intensive properties. Extensive properties are dependent on mass. Okay. So, intensive properties are color, temperature, boiling point, they do not depend on the mass. The luster, the hardness, they do not depend on the mass. You can have a small item, you can have a large item, the hardness will be same. You can have a boiling point, you have a small, you put 1 kg of wax or 10 kg of wax, the boiling point is the same. When you try to do extensive properties are nothing but volume, mass, size, weight, length. These are all extensive properties where it depends on the mass. Please try to understand specific properties, intensive properties and extensive properties. Extensive properties do depend on the amount of matter that is present. An extensive property is considered additive for subsystems. Volume, mass, size, weight, length, energy. The ratio between two extensive properties is an intensive property. Between two, volume by mass, volume by size, volume by weight, volume by length, energy, length by energy, length by weight. So, when we talk about it, two extensive properties, when you try to take a ratio, so volume by mass, volume by size, volume by weight, volume by length, volume by energy, right, or you can try to have weight by length, weight by energy, right, weight by mass. So, you can see that. So, the ratio between the two extensive properties is an intrinsic property. For example, the mass and volume are extensive properties, but their ratio density is an intrinsic property, intensive property. What is intensive? Which does not depend on the mass, independent on the mass. Okay. Intensive properties. Intensive properties are bulk properties. which means they do not depend on the amount of matter that is present. For example, boiling point, odor, luster, density, melting point, hardness, a state of matter, temperature, ductility, color, refractive index, maniability. All these things are intensive property. The ductility of a given material, you can draw a wire. Malleability means you can draw into a sheet. That does not depend upon the mass. So, that is what is intensive properties. Let it be 2 liters, let it be 20 liters, let it be 200 degrees Celsius, let it be 100 degrees Celsius or 30 degrees Celsius. The boiling point will remain 100 degrees Celsius for a given item. So, this is intensive and extensive properties. So, the overall properties, what are they? So, the most important one is T, P, rho. T is temperature, pressure, rho is density, boiling point, specific volume, specific internal energy will always represented by U. Then you have a specific kinetic energy Ke, enthalpy as a small h, and color. When we look into extensive properties, volume, internal energy, kinetic energy, potential energy. So, energy, there are two things. Na? One is Pe, which we have seen already, one is Ke. Right? So, energy, then you will have potential energy, kinetic energy, mass, weight, and length. So, let us see the comparison between extensive property and intensive property. Why is it very important? Because many a times when the conversation happens, people try to mix up extensive with intensive properties. So, you should be very clear. When you solve a problem also, you should know we are trying to use this. Maybe in the examination hall, I would have given extensive property and for in which you derive and then get an intensive property, so that then you can try to solve the problem. So, extensive properties are dependent on mass of the system. They are additive. Its value for an overall system is the sum of its value of the parts into which the system is divided. The examples are mass, volume, energy, and enthalpy. Uppercase letter are used for extensive property except mass. When we go for intensive, these properties are independent of mass system. These properties are not additive. So, here it is additive, here it is not additive. Its value remains the same whether one considers the whole system or only a part of a system. Please understand, these two properties are very, very important for you. So, you try to take a total dabba, inside you take 1 unit, it is the same. So, it remains the same whether one considers the whole system or only a part of the system. Pressure, temperature, density are part of it. Lower casing are used to intensive properties except pressure and temperature. Now, let us move into the other basic concepts: thermodynamic state, path, and processes. So, thermodynamic state is very important. Path and process is very important when you look at cycles and other things. So, let us understand what is a state. It is the condition of a system as defined by the values of all its properties is called the state. It gives a complete description of the system is the state. Any operation in which one or more properties of the system change is called as the change of state. From one to the other is called as change of state. For example, solid to liquid, change of state. Right? So, it is the condition of a system as defined by the values of all its properties is the state. It gives a complete description of the system. Any operation in which one or more properties of a system changes is called as change of state. Path and process: a series of state through a system passes during a change of state is the path of system. If the path followed by the system during the change of state is specified or defined completely, then it is called as a process. So, for example, solid to liquid. Right? So, if the path followed by the system during the change of state is specified or if it is clearly defined, then it is called as a process. So, path and process are linked. A series of state through a system passes during a change of state is path. So, you should clearly understand the difference between state, path and process, because this will be used later while solving problems.
we can allow one of the property to remain a constant during a process. Now we are trying to look at process. Now from a process we will go to cycle. So that we will see later. So is that clear? Path, process. If the path followed by the system during change of state is constant or is specified, then it is called as process. So now we can allow one of the properties to remain constant during a process. For example, isothermal. One of the property you should understand. Constant during the process. What is a process? You have understood process here. So for a process you should understand the path, right? So isothermal. When we say isothermal process, then that means to say there is a constant temperature. Isobaric means constant pressure. Isochronic means constant volume. Isoentropy means constant entropy. Isoenthalpic means constant enthalpy. So these are some of the most important properties you should understand. Isothermal, isobaric, isochronic, isentropic, isenthalpic. A cycle. So now state is done, path is done, process is done. Now we are trying to see a cycle. Cycle, when a system in a given initial state undergoes series of process and returns to the initial state at the end of the process, then the system is said to have undergone a thermodynamic cycle. For example, it starts from a solid, it goes to a liquid, then from a liquid it goes to a gas, and at the end of the process if it comes back to solid, that's called as a thermodynamic cycle, right? Or you can have a cycle between PV diagram, you can pressure and volume, you can try to have something, the process goes this way, this way, this way, this way and comes back to the starting point. Right? When the system in a given initial state undergoes a series of process, what is a process? I am redefining. If a path followed by a system during change of a system is specified, then it is called as a process, right? So this is a cycle. State and path function. State function means a property whose value does not depend on the path taken to reach that specific value is known as state function or a point function. From 1 to 2, from 1 to 2 it goes, right? So a property whose value does not depend on the path. This is a path taken to reach the that specific value is known as state of function, state function or a point function. So it can go through stage like this, it can go through a staircase effect like this, it can fall up and down, it can lose energy, but finally it is called as a state function. A state function are systems where only the start and the end points matter rather than the path. So it is like your drilling experiment. You have a hole to be made here, hole to be made here, hole to be made here, here. So you have to make 4 holes. So it is least bothered how do you go. You can go like this, 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 or you can go like this. Then from here you can go like this, then you can come like this and you can finish. So the state function are systems where only the start and end matters. In between path does not matter. That is a state function. Whenever there is a change in any one of the macroscopic property, the system is said to change into a different state. Thus, the state of the system is fixed by its macroscopic property. Clear? This is very important. The state variables. Let us understand what are different types of state variables. The state or condition of a system is described by certain measurable properties, and these measurable properties can be defined as a state variables. Whichever parameter you can measure, it is called as a state variable. Pressure, volume, whatever, temperature, enthalpy, all these things if you can measure, it is there. So it goes from P1 to P2, V1 to V2, N1 to N2, G1 to G2, H2 to H1. So you can see all these things. So state variables, the state or the condition of a system is described by a certain measurable properties, and these measurable properties are called as state variables. Because later when you try to work on PV diagram. It basically, when you try to take an IC engine, there is a play up between pressure and volume. So then you will try to move your graph from one position to other position to other position to other position. You will try to move, right? When you try to move, so then you will try to measure the state variables, right? So what happens? P1, this is P1, this is 2, this is 3, this is maybe 3, 3 you can say, or 1, 1, this is 2, right? So the pressure will be the same, the volume increases. So P1, P2, V1, V2. The state variables or the thermodynamic parameters depend not only on the initial and the final stage of the system and are independent. How the change is brought are called as the state function. So now state variable, measurable quantities are state variable and state functions are the independent. So our state variables or thermodynamic parameters depend only upon the initial. It's not only, it's depend only upon the initial and the final state of the system and are independent. How the change is brought is called as a function. Note, state function depends only on initial state and final state of the system. It does not depend on the path or how the process was carried out. So some common state functions are internal energy, enthalpy, entropy, free energy, pressure, temperature, volume, etc. So state function is very clear. The definition for state function are independent of how the change is brought are called as state functions. So these are different types of state functions. So pressure is P. Pressure is nothing but force acting per unit area, is a measure of a average force exerted by the constituent molecules per unit area on a container wall is called the pressure. The pressure does not depend on the path of the molecules, thus it is a state function. What is a state function? We have defined it here. How the change is brought is called as a state function, independent of how the change. Temperature is defined as a measure of average kinetic energy of the atom or molecules in a system. The temperature measures a property of a state of a system irrespective of how it got there, and thus it is called a state function. Clear? The temperature says 32 degrees Celsius. It does not say I moved from 25 degrees Celsius to 32. No. So that's what is the temperature is defined as a measure of average kinetic energy of the atom or molecules in a system. Volume. It is the amount of physical space occupied by the substance and will not be dependent on the path followed. Thus, the volume is a state function. Mass, the measure of the amount of matter. Here, the space. Here it is the amount of matter in an object is called the mass and is usually measured in grams or in kilograms. Mass measures the quantity of the matter regardless of both its location in the universe and the gravitation force applied on it. Thus, it is called as a state function. I am trying to tell you what are all the state functions. Then it is internal energy. Internal energy is, it can be defined as a sum of all kinds of energy associated with the molecular motion. The internal energy of an ideal gas is a function of temperature only, according to Joule's law, and the internal energy of real gas is a function of temperature, pressure and volume. So it can be seen, since internal energy depends on PVT, which are a state function, the internal energy also is a state function. So we have seen P, V, T, M. Now we are seeing U, then we will see Gibbs free energy, and then we will move to entropy and enthalpy. Gibbs free energy is the enthalpy of a system at any given point minus the product of the temperature times the entropy of the system is Gibbs free energy of a system. So it is given as G equal to H minus Ts. So it is enthalpy of a system at any point minus the product of temperature and entropy of a system is nothing but Gibbs free energy of a system. The Gibbs free energy of a system is a state function because it defines the terms of thermodynamic property that are state function. Entropy is a measure of imbalance in a system and it totally depends on the path through which the system has achieved that state. Also, it is unique to the current state of the system. So that is entropy. So enthalpy, entropy. After finishing the state functions, now let us see path functions. Path function depends on the initial and final state of a system, and also it depends on the path of the process which is followed. So, that is the path function. State function, I would just like to rebrush. So, you would have seen state functions: pressure, temperature, volume, mass, internal energy, enthalpy, entropy. You have seen all those things. Now, path function. So, what is an example? Example for this is heat and work. So, different paths give different values of the system. So, here I have written very clearly, depends on the path of the process followed. So, path function requires multiple integrals and limits to integration to integrate the property. I repeat, path function requires multiple integrals. We are taking small and then doing it, and limits of integration to integrate the property. It depends on the specific process or path and work, heat and other energy transfer forms. So, path function looks into initial, final plus the path of the process.
I hope you enjoyed this lecture. Thank you very much.